Okay, so moving on from understanding what carbon dioxide is and how it plays within the global environment and what we're trying to solve, we need to start to dig deep into the life cycle of a building now, so we can start to think about how it's going to apply to you in your profession. So we want to understand the whole life carbon cycle. Okay. We're going to be looking at materials. Where do they come from? How do they arrive on site? How the construction process is run from start to finish and where energy comes into it. The building itself uses energy for its entire life. And then, of course, at the end of the life, given we are only on this planet for a blink of time, whether that's 50 years or 500 years, at some point these buildings will be recycled. Let's face it, the dinosaurs were around 35 million years ago. We're talking about periods of time that are just fragments. So, the whole life carbon assessment provides a true picture, notice I've highlighted that here, of a building's carbon impact on its environment. That's what we're digging into. When we really get to grips with that, we can start to design things that are actually going to have a positive impact on the planet and steer us away from climate change. So, let's take a traditional product, a brick. Okay? Where does a brick come from and how does it arrive on site? What's the energy within this? So first of all, the materials get dug up and out of the ground. So this is a clay brick. So clay is mined from a quarry. Okay, they're sorted and filtered into appropriate material for actual use, discarding any waste that's not good enough to go into the mix. Mixed with sand and water and cut to shape. Once it's cut to shape, it goes into a drying oven. This is where it really kicks in. So we've been using fossil fuels at the beginning here because the machinery in the quarry has been operating and emitting carbon dioxide from it. And now we're into heating up this brick. So this particular example suggests 36 hours that the brick needs to be in a hot kiln. Imagine running your oven at home for 36 hours. How warm is your kitchen going to get if it was just baking away? And we're doing that with every brick that we put on a building site. So once the brick's been cooked, it's then moved to a lower heat area where it can cool. Once it's cooled, we then package it up and ship it off to site. All these processes of moving this heavy weight about are consuming energy, and therefore we're emitting carbon dioxide into the environment, whether it's from an electrical source or whether it's from a fossil fuel source like diesel for the machinery or diesel for the lorry driving it out to sites. Once the brick arrives on site, what's going to happen? Well, it's going to get moved into position. In this example, they're using cranes to move materials around, which again, it's using energy. Imagine how heavy that one pallet of bricks is. If you were to carry that one brick at a time or 10 bricks at a time, depending on how strong you are, up a set of ladders to get it from the back of the wagon to where it needs to be. Think how much energy you personally are going to consume. How much food are you going to have to consume to move those bricks from A to B? So we're using energy around the building site to move these materials about. Then the contractors come together. Bear in mind, those contractors have driven to work most likely, or ridden public transport, but one way or another, there is a carbon footprint associated with them being in the same place as the bricks to actually build this building. They then turn on the cement mixer and they take the cement. And the cement, that also has its own carbon footprint because that's been through kilns and that has required a considerable amount of energy to be turned into cement that's usable for a site. So we mix the cement and the water to create your mortar, and then we build the building itself. So lots of energy goes into construction. Once the building has been built, the building then lives for a period of time. Like I said, whether it's 50 years, 100 years, or 500 years. Every day that that building is in use, it is using energy. The biggest problem we have in this country is that our buildings require lots and lots and lots of heat energy because we've never built them well insulated and airtight so that we can reduce the amount of heating energy needed. So in an old building, as you can see, this red section here is indicating the heating energy. Blue section is to heat the hot water. And the yellow section, your household energy. So running the lights, running your appliances, your computers, anything like that. Household energy, hot water, heating. They are your main consumption of energy. As you can see, in a traditional house, we use lots and lots and lots and lots of energy for heating. If we just step back and look at the UK as a whole, transport and buildings, the built environment, so your arena where you're developing your professions, use the most or output around about 2/3 carbon dioxide between them, and they're about even. So transport and logistics against the built environment. And built environment, your buildings, they on a daily basis, the majority of the energy, so the majority of the carbon dioxide that's kicked out into the environment comes from heating our buildings. We have to learn about reducing that heat consumption, and that's what we'll progress into in this course as it goes. And that's where you can really, really develop your skills and your abilities to be able to offer customers in future the opportunity to show them how to build sustainable homes, reducing the heat energy. Down here, we can see that this is a passive house, so its energy consumption is shown to be so much smaller than a traditional house. Okay, and there was a reason that I actually picked this particular image that I wanted to share with you, and it's this description. So below this is line 0, and this line 0 must be representing the amount of energy that a house needs for occupancy to live on a day-to-day. We're not talking about the energy now that has gone into the brick and building the building. We're talking about the energy that we use on a daily basis. They've put it as net zero. And my question is, what does net zero mean? And hopefully, with this course, and particularly today, we're going to try and debunk the fact that net zero is a phrase very casually thrown around. So in this example, I think what they're trying to say is that this house uses or creates, they say that they've got PV, so photovoltaics, otherwise known as solar panels, on the house. In fact, we can even see it on the little picture. I think they're trying to say that this house creates more energy than it's using. So it's net zero. But that is a phrase that has been chosen by the artist of this picture. There is no standard, and there is nothing to say when the word net zero can be used or not be used. Some people use carbon negative, carbon neutral. There's lots of phrases to try and communicate this message that this building here creates more energy than it uses on a daily basis, and therefore will be exporting energy back to the grid if it's set up like that. Okay, so buildings consume energy. At the end of the life, and let's just sort of rewind a little bit. We've got our materials like a brick. They've come to the site. The house has been built. The house has been lived in. But at the end of that, the house is going to get demolished. And I say house, this applies to all buildings. Because let's face it, how we live today isn't how they lived 30 years ago. How we live today is not going to be how we live in 30, 40, 50 years or even 100 years' time. So although we will try and design and build houses to accommodate the way we live now, there will become a time where our houses won't be fit for purpose. They won't suit the way that we live. As you can see from here, we've got a selection of materials in this demolished building. A lot of steel reinforcement, concrete, bricks. There is now going to be huge amounts of energy going into sorting that out. It has to go somewhere. Or it just goes to landfill. If it just goes to landfill, it's a complete waste of energy because don't forget, we made it initially. We created a usable product. We've only used it for a blink of amount of time, our life, and then we've just demolished and disposed of it. Okay, there is a big carbon footprint associated with just demolishing buildings and getting rid of the materials. Because what will we likely do in place of this old building now that's been demolished? We'll bring in a new team of builders and build a new building all over again. creating more carbon. So understanding whole life carbon cycle. Picked a couple of graphs here. Now don't get put off by these graphs. We'll talk through them now. And what we're trying to establish is why it is important to look at a whole life carbon cycle, why it's important to design buildings to be low energy when it comes to the embodied. So thinking about how much energy goes into the building materials right at the beginning and how we build those processes and the transport of those materials. Why it's important to construct buildings with low embodied energy. Why it's important to consider how much energy is needed in a building to live. And why it's important to think about the end of the life. So let's have a look at these graphs here. There's a small red line here which is indicating the 0. Each time we do something, we're adding energy, okay? So first thing that we did was we built the buildings. These are all the materials. So we've got concrete, mineral wool, oil-based materials, plastic materials, timber, general construction materials. So they're adding up. Imagine that as a stack of carbon. That's how much carbon is going into this building, okay? Then during the life of that building, we run our appliances and we heat the building and we use up more energy. So we can add that lump of carbon energy to this stack. Okay, and then at the end of the life, we bring in the big heavy machinery and we demolish it. We transport it to wherever we go. We put it through a recycling process and we create energy. We use energy in that process. Now below the red line is where things get interesting, because here you'll see that this is timber store. Now this is an example of a timber frame house. Let's go back to the first lesson. We were talking about photosynthesis and we were talking about how trees grow. So trees reach out into the environment, they pull down the carbon dioxide, release oxygen, and create the starch that they use to grow. And in doing so, what they're doing is they are locking up carbon dioxide that's been extracted from the environment and putting it into itself as a plant. And that is a carbon store. So we are literally, with trees and plants, pulling in carbon dioxide from the environment, reducing the amount that is up there in that greenhouse effect, and bringing it down and into the tree itself. So if we were to use trees to build with, then we are actually storing carbon. Now you might say, but you're chopping down trees. Okay, so there is some energy used in going to harvest a tree and turn it into a usable material. But the tree has actually locked away significantly more carbon than the amount of energy needed to turn that into a building material. And this is where it then gets exciting, because what we do in place of the tree that has grown, a full-grown tree, is we plant a new one. New growing trees can lock up a lot more carbon than an old tree that's not growing or is growing extremely slowly. So planting new saplings, growing them, harvesting them, and planting new ones, it's a great way of starting to collect carbon. So by using timber, we can actually have a negative impact on this stack of carbon and start to bring it in. This last section about the benefits is talking about things like solar panels or wind turbines or air source heat pump and ground source heat pump. Lots of different renewable energies that we put a small amount of energy into and we get more energy back. So the benefits here are from our renewables. The tree is locking up carbon, and if you add that to this stack, bearing in mind it is negative, we end up with something like 200 kilos of carbon dioxide per square meter for a building. So we reduce this amount. In an ideal world, what we would see is our buildings, yes, they would have energy consumed, but below that line, we'd have as much energy from benefits or carbon stores, and that would bring us down to zero. That would be a net zero house, in my opinion. That would be one phrase you could potentially use. Let's just take a look at this graph here. Okay, zero is down here, and this is how many carbon tons are being emitted into the environment as we build a building and as the building lives. We've got 60 years on this table here. Okay. So on day one, and I'm just going to pick this green line here, which is a proposed construction with renewables. Okay. So when we build it, maybe it's been with this system here. So there's been so much carbon emitted in the construction process. And it's got renewable energy on, so it's just ticking along. So it's not really emitting much in terms of carbon dioxide into the environment because it's got benefits from things like solar panels, wind turbines, and other renewable sources. The problem with buildings is our mechanical things and our materials, whether it's a kitchen, a bathroom, boilers, ventilation systems, solar panels, they do have a life expectancy, and they're generally much, much shorter than the building itself. So when we get to about 25 years here, the owner of this building has come along and done a renovation. And in doing a renovation, they've added to the whole life carbon footprint because they have bought new materials, they have done the processes, they have used energy to upgrade their building. And again, we see that happen at around 50 years. And at the end of the life, we see a spike. And that spike is caused by the demolition and recycling of those materials. So, why is it important to measure the whole life cycle? We hear people talking a lot about renewable energy, but renewable energy only really looks at this little section here, which is this very steady gradient here. It shows how much the building is impacting on a daily basis. People are forgetting, and you might call it a false economy, that to put a building in place, it consumes a lot of energy. And to demolish a building, it consumes a lot of energy. So we need to take a holistic approach and look at the whole building, including things like renovations and upgrades, to see how friendly that building is going to be to its environment. Okay. Let's just do a quick recap then. To get materials to site, they have to be manufactured, and there's a big lump of energy there. To build a building, there is a lot of energy goes into it. To live in a building or work in a building, a big lump of energy goes into it. And to demolish the building, further lump. Add all of those lumps together and you get your whole life carbon footprint for a building. Now we know what we're working with. Now we can start to make sensible decisions about which materials we're going to use, which renewable energy systems are appropriate, and how we make a building sustainable. Remember, it's about a true picture of a building's carbon footprint, not just whether or not the energy coming through maybe a solar panel is more than the energy that's being used. A timber frame building is going to be a lot friendlier to our environment and contribute far less. In fact, it's got a positive contribution when it comes to global warming, the greenhouse effect, and climate change, versus concrete building, which would have huge carbon footprint, even if that building, concrete building, was built as a low energy building, meaning it didn't need much energy to heat it and for people to live on a daily basis, because it is possible to build from materials that are not environmentally friendly, buildings that are still low energy and people might argue are sustainable. And it's up to you to understand what sustainability means, what zero carbon means, what net zero, and all these different phrases mean, and understand what questions you can ask. So you can differentiate between concrete building of traditional concrete. There are some eco-concrete starting to come to the market, but again, we question the embodied footprint of that product. And in questioning those products that are going into the building and looking at its energy use through its lifetime, you can start to make your own educated decisions.
Excellent, Dave. So a real take-home point there is the whole life cycle carbon assessment when looking at products. And one of the things I just thought I'd mention is solar panels. Just talk to us a little bit about the waste of a solar panel, at the end of its life cycle.
Okay, yeah. So let's dig into it. We looked at the brick, didn't we, to start with? The energy that goes into making a brick and putting it through a kiln. Let's look at a solar panel. So solar panels are made of basically glass and silicon. To get glass, you have to put it through a kiln. Lots of heat energy goes into it. And it really does have a big, dirty carbon footprint. So when your solar panel lands on the roof of your building, it's already carrying a really big carbon footprint. It's then going to have to work hard over the years to create sustainable, renewable energy from sunlight to offset the original carbon footprint. Now, it might be reducing the building owner's electricity bills because they're not actually drawing from the grid, or maybe they're contributing to the grid. So economically, it's got a great impact there, but it has to offset that original carbon footprint to start with, and it takes a number of years. I showed you that buildings do need upgrading and renovations, maybe every 25, 30 years or so. And solar panels typically have a life expectancy of about 25 years. We've recently looked at doing an assessment of whether it is good to get rid of the solar panels and buy the latest technology and put new ones on, or to let the solar panels stay there for 60 years. Over time, solar panels deplete in performance, so you might argue that it's better to get new ones, and financially, maybe you would make more money from new ones. But the return on the energy that they create, although it might be less in 30 years' time than it was when they were brand new, it's still significant. I think it's around about 80% of its original performance. So to keep the solar panel for twice as long, maybe say 60 years, if it will continue to operate for that period of time, would be more sensible from a carbon footprint point of view. And at the end of that, and we're now getting to a place where solar panels have been on buildings for 15, 20, 25 years now, and very popular. We're starting to get our first wave of waste. So these solar panels are now coming down from the roofs, they're coming out to the fields, and we have a huge problem on deciding on how to recycle them. The product itself is not very recyclable, and therefore it comes with another carbon footprint.
Great stuff. So we are starting to learn more and more about these renewable products, because I think a lot of people misconstrue, I've got a renewable product, so therefore I'm environmentally friendly, but there's more considerations to take into account. Performance reduction you've mentioned,